Hi, Chris. Hi. How's it going? Good. Maybe you can ask yourself.
Yes. The president. He's a secret.
That's probably what happened.
Member of Parliament. 1856.
Well, I joined in 1966, but I wasn't just continuous. I was separated and later around 1992. And I came here, I was in Vancouver. I came here.
This one, way down there. Good evening, everyone. We'll get started in just a moment.
I know. It's a good idea to share. No, as you know,
Good evening, everyone. I'd like to welcome you to the September monthly meeting of the Royal Astronomical Society of Canada Victoria Centre. I'm Chris Pearce, the Centre President, and I understand we have some visitors here tonight, so welcome to our meeting, and hope you enjoy interacting with us. I think we're a fun group. Maybe not for me to say. Tonight we have a extraordinary general meeting that will take place shortly. As you probably have read and has been distributed by email a few times through the summer, we are required to submit new bylaws under the amendments to provincial legislation. So we will be considering those shortly. I think we'll forego the observing reports tonight. Should be on our normal agenda. Then we'll have some announcements, talk about some upcoming events, and then we'll have our guest speaker, which is the real reason we're all here. And just to remind you that there's coffee, tea, and cookies in the Elliott Building 4th floor lounge after the meeting for anybody who'd like to stay and partake. Our favorite part. So I just wanted to mention that under our current bylaws, a quorum of the centre is 3 members. So we duly have a quorum assembled. So maybe I could call Nelson forward to help with the next portion, which is the extraordinary general meeting. And we'll do that. I don't know if you want to come up here or be there or whatever. Nelson chaired the endeavor to replace the bylaws. And so he's going to say a few words about what that involved.
Thank you. Can you hear me okay? Do I need the microphone?
You want the mic? You're good?
Yeah, I should. I don't know if I can
project.
the notion of redoing our bylaws began a couple of years ago. I don't remember exactly how long ago, but there was national legislation that had to do with the Societies Act, and it filtered its way down to provincial revision of the Societies Act, which filtered its way then to nonprofits and other societies, informing them that within a couple of years they were going to have to redo their bylaws and submit them. And so we sort of began that process at that time. There was a committee of 4 of us, was Les and Jim Hesser and Chris Gaynor and I undertook to create this new set of bylaws. But because it wasn't due for another couple of years, we weren't taking it very seriously. And about a year ago, or maybe 9 months ago, it occurred to me, having been a lawyer in the far distant past, that maybe I'd better get to working on this thing. So I had in the early days, sometimes accompanied by Jim Hesser and Les and Chris Gaynor, I had gone to some meetings that were put on that had to do with the Societies Act and new bylaws. We went to a couple of seminars. We talked to the I then talked to the corporation division. It turned out that the seminars and things we went to weren't very helpful because they focused more on the changes to the Societies Act itself and had very little to do with the creation of bylaws. So when I really hunkered down and was trying to figure out what I would have to do to create bylaws, or what our committee would have to do to create bylaws, I went to, there happened to be someone in the Vancouver Centre had prepared bylaws. So I read the Vancouver Centre bylaws, I read the Ottawa Centre bylaws, and the National RASC created model bylaws. So I used all of those, took all of those into account, and British Columbia, the government of British Columbia, also created model bylaws. Now, the model bylaws of British Columbia, which you would think would probably be the best ones, were the least useful. They were about 4 pages long, and most of the 4 pages consisted of blanks to fill in. So, using what I have described, the information I have described, and with the assistance of this list of people who I could not have done this without, I will turn this over to Chris. Jim Hesser worked on this from the very beginning. Les Welsh worked on it in the beginning. Chris Gaynor worked on it and stayed with it the whole time. Joe Carr. Sid is an incredible proofreader. And Bruce Lane helped. And there's probably other people that I have forgotten, but I created a set of bylaws. They're quite, this is the original bylaws. These are the ones that we're replacing. These are 18 pages long. I created new ones, and they happen to be exactly 18 pages long. And this is them, and you all have a copy of them. And we submit them for your approval.
Thank you, Nelson. So I'll call this part of the meeting to order. We have basically one item of business in the meeting, so I'd entertain a motion to adopt the new bylaws. Sid, thank you. And a seconder? Dorothy? Dorothy Ball. So any discussion on the motion? Yes.
What's the big difference between the old bylaws and the new ones?
Nelson, did you want to speak to that? Well, maybe I'll just start off by saying, well, one thing is the society was quite different in 1981, I believe, our old bylaws are from. So.
I think the big difference is the way that they require that they be filed. In fact, I don't know that the society governance people are really looking at file. The thing that they're mainly concerned about is the Constitution. We had submitted a constitution back in the 80s or 70s, whenever this thing was filed. And our constitution has to remain unchanged. We cannot change it by voting this organization. We would have to go through the whole process of restructure, or at least the acknowledgement of a restructure of our goals. With this, when we submit this, our constitution will be submitted in an identical copy of what we had originally submitted. The bylaws are just sort of the tail that go in behind this, behind the constitution, and whether or not, I mean, it forms the system of governance for us. It tells how we conduct meetings, it tells how we elect officers, and all those things you'd expect to find. But whether or not they want to look at it, I have no idea.
And I would say one other, where I was going with that too, is that the centers, I think at the time, were responsible for their own memberships. So there was a lot of details about how a person became a member of the center, which is now centralized through our national office. So basically, it's either submit documentation to Toronto on paper or online. And so there isn't a center function per se. So that was, people were proposed and.
In addition to his code of conduct.
Yeah.
It was not there in the original.
Right. Yeah. Any further questions?
Just a reminder, Chairman, we need to remind the audience that just members vote.
Right, thank you. Question? Okay, hearing no further, I'll call the vote. Please, members only. All in favor, please raise your hand. Opposed? Thank you. So, motion to adjourn the extraordinary general meeting. Bruce, thank you. Okay, we'll move on. Thank you very much. So we'll get that filed and into the works there. So the next part of the meeting, for those who are first time here, or it's been a while, is some announcements. So I don't have too much else to announce other than I did displaying up here the RASC 150th anniversary stamps that are available. So you can get a booklet of 10 or this sheet of 2. I just decided to get some, and apparently there's some features in the black light which I haven't looked at yet. Have you seen those, Jim? No. Somebody mentioned that if you shine a black light on it, you see something else too. So one of those pictures is by
Alan Dyer.
That's it. I knew I'd forget his name, and so it's very nice to see those. Oh, there it is, right there. Yeah, this is the Northern Lights photo. The membership is at 278 the last time I checked. So we're holding fairly steady there. 2 more things that I'll mention right now is we are taking orders for the 2019 Observers Calendar. We're on a fairly tight timeline because we'd like to get them before the November meeting. So you need to let me know by September 24th, I think I said, the Astro Cafe that night, or you can let me know tonight. You don't necessarily need to pay for your order today. They are $15 each. If you buy them yourself, you will actually pay more than that, plus shipping. So it's about 2/3 of the price it would cost if you ordered one directly. So I'll encourage that. Our November meeting is the annual general meeting, and that commences with a dinner. Remind everybody that the meeting portion, which is like this, is open to the public, open to everybody. However, the dinner is at a fee. The fee will be $40 again this year. The dinner consists of a buffet with a pre-ordered entree. The entree choices are chicken, salmon, steak, or vegetarian ravioli. So if you'd like to attend the dinner, please let me know, and I'll need $40 from you at some point. So I think that's all I have. Reg.
Hello, everyone. What I have here is the 400th edition of the Sky News. How about that? Now, the motley crew that's on the cover here crashed one of our DAO star parties, and they're a group of actors largely from the Phoenix Theater, and they put on a great performance. But when I sent out the message via email, I had an error. I called them the Cosmic Misfits. They actually are the Zodiac Misfits. I apologize, and it's corrected on the web version of this article. So there you go. Check it out, please. And I have a limited number of hard copies if anyone wants one at the end. See me at the end.
Great. Thank you, Reg. Deb, anything further from the follow-up from the Star Party?
No, just all tidied up, and we're going to hopefully publish a guide protocol for the next people who put on the Star Party, because although we were rushed, we had very little time. It came off, but there was a lot of extraneous exchanges that needed to have been and caused confusion. But we'll fix that for next year, and also we'll order the right weather.
Yeah, that would be very helpful. Yeah, I think the new site has a lot of potential. We didn't get to actually test the skies much this year, except for Diane, because we got kind of rained out some of the time and certainly clouded out most of the time. So we'll, but if they'll have us back, I think we'd like to try it again, and hopefully under better conditions, and try and set a date that maybe we can, I don't know, get some good weather for. Who knows? Okay, secretary and website, Joe.
The website is going along fine. I don't think there's anything to report there. I do have some Star Party t-shirts for sale. If anyone would like one, please let me know. Black ones are $16, and I have one white small for $12.
Great, thank you. Maybe I'll just mention too, we got a donation of some books that will be added to the library, so that's what this box of books is. The Night Sky Observer's Guide in 2 volumes, and Eurometria in 3 volumes. And that was from a former member's estate. Treasurer Bruce, after a bit of a spending spree on the Star Party.
Went a little crazy go nuts, but we still look pretty good. Our members account is at 13,133. Gaming account at 20. We'll be wrapping up our expenses for the year at the end of this month. So if I'm writing checks to you, please cash them by the end of the month, so the bookkeeping is pretty good as it could be. Thanks.
Thank you, Bruce. Outreach coordinator, Ken. We've had some busy summer.
Had a busy summer, yes. Hello, I'm Ken. Everybody remembers Astronomy Day. I think we talked about that before we left for the summer. There was over 800 people there. Strawberry Festival, it was quite busy. It was a nice family event. That was in July. We had about 750 people go through our area in about 4 hours. It was quite popular. Fort Rock Hill after that in August, and there was 239 people attended that. The gates opened at 8 o'clock, and there was a lot of campers, overnight stayers for that. Scott gave a nice talk for that. It was a nice family event. You might want to consider that next year if you're going to do that. And Saturday Fair, everything went off good. We had 3 days of fun. I think Lori said there was 30 people involved who volunteered for that for the 3 days. And I think there was just over 2,000 people came through our area, which is very close to last year's. I think all we have left is the Fairfield Community Fair. That's on the 22nd, Saturday the 22nd. Fairfield gives us a really good deal on the community center. So if you want to come out and support us, that'd be great. Thank you.
Thank you, Ken. Schools program, Sid, I guess it's starting to get bookings.
Yes, we have few, but it's too early to report.
Yeah.
So really, there's no report at the present time. But maybe next
Time, yeah. National Representative Nelson. So there was a General Assembly in Calgary over the Canada Day long weekend.
Yes, I don't have anything to
say about it, other than that I would urge people, if they can at all swing it financially to go to one of these things. It really gives you a lot of insight into what our club does in a general way and what it does nationally. The principal serious object that was discussed at this General Assembly was whether or not the national representative group, the National Council, which is a combination of national representatives like myself from each center and the officers of the national RASC, whether it should be organized to include some group other than national counselors. For example, the officers of RASC and club presidents, or the officers of RASC and nobody. And that was debated at great length in the National Council, and it was the suggestions of national officers were defeated, and the senators have retained their representation in the same way that they had before. And I would probably have the meetings that we have with that group, 2 of the 3 meetings are by phone, and the last meeting of the year is going to be Sunday in the teleconference. So if this was after that, I would have
more to say. At that meeting, I'm pleased to announce for those who don't know, Chris Gaynor has become the national president of the Royal. And looking back through the names, it looks like it's been 40 years since we've had a senator or the national president, since Alan Batten. He's still a member of the center and was the one previous who was president. Matt, anything on the technical front?
Yeah, a couple things to report. Over the summer, we bought some Thatcher ants,
Okay.
wasps, but everything's okay. We have a new roof coming for the sprocket box on the outside, getting that fabricated. It's been bugging me for a long time, so it'll be good to have that taken care of. And on a more telescope-oriented side of things, we have electronic focusing, which is now repeatable. So the computer can pick the best focus for us. We can do this on an ongoing basis through an observation. Say every 20 minutes or so, every number of exposures. This will improve the situation for capturing good data. And also we have, in addition to that, for focusing a batten-off mask on the way for a 16-inch size telescope. The previous one obviously did not work. As well, a panel which we intend to mount on the southern wall for generating flat field calibrations during any weather, any time of day. Typically, you would have to do that in the twilight. So, a couple big improvements there. More to come.
Great, thank you very much. And Michelle isn't with us this evening, so we'll move on. So, some upcoming events then. Remember, if you're an active observer, and we are switching to Saturdays, correct? Is that right? I hope I got that right. So the observatory will normally be open on Saturday evenings. So you need to be on the active observers list to take part in that. Please let me know if you want to be added to that list. Astro Cafe resumed on Monday after its summer recess. And so that will be every Monday evening through May, with a few exceptions, I think around Christmas, otherwise we'll be carrying on. That's a really great event if you haven't been. That takes place in the Fairfield Gonzalez Community Association buildings on the grounds of Sir James Douglas School in Fairfield.
And it's open to the public.
So everybody's welcome. The Friends of the Dominion Astrophysical Observatory are having their annual general meeting on Saturday evening, and they have invited everybody who's participated in the summer star parties as well. As Ken mentioned, we've got an outreach event for Fall Fairfield Fete, I think they call themselves, or the fair, on Saturday the 22nd. And there's also an event that Dorothy is involved in that day as well. So I don't know if you wanted to say a few words about that.
Well, this is at the George Nature House. We've been invited actually several times to engage with them, the RASC. And if it's clear, the announcement will be out, and we'll have night sky viewing after a talk, after starting with refreshments, hot drinks and sweets at 6:30 at the Gorge Nature House. And there's a nice place, nice concrete surfaces to set up telescopes. And so after, and then the talk, by yours truly, my arm got twisted. And then on life flight and their influence on the evolution of our planet. And then night sky viewing until 10. And so I won't mention them because I haven't reminded them, but 2 people have promised to be there or said they would be there at least if it's clear. But if you keep that in mind because it's going to be advertised that way and we would need a few telescopes. And it's a really nice place which we might want to consider for a regular, occasional public outreach, as they would definitely be interested in doing. So that's the evening, the 22nd.
We'll send out some more information by email about that, so you don't have to try and remember it. But basically, it's in the Esquimalt Gorge Park. And I've already mentioned the annual general meeting dinner, so please let me know about that. And I think that is everything I have. So maybe Rach, you could. Oh, Bruce, sorry.
We should bring up for people who want to run for council.
Oh, right.
Consider that. We even strongly consider that.
Yes.
Upping your participation in the RASC Victoria, should you wish to partake in our monthly and sometimes bi-monthly council meetings.
Yeah. Oh, right. Thanks. Yeah, so maybe I'll just follow up on that. Yes, thanks, Bruce, for reminding me because I didn't write that down. Sherry Butner, our president, is in the process of contacting current council members to determine their interest in staying on or leaving their current position. But anybody who would like to join the council would be more than welcome, and so I recommend contacting her if you're interested. So that's pastprez@victoria.rasc.ca. Sorry, and Jim's announcement. I forgot about it. Jim.
They just suggest people save the date, Friday, the 16th of November, so the night before the annual general meeting and a good dinner. Michael Jarvis, in partnership with Christchurch Cathedral, is creating another one of his Intimate Encounters concert. There was one in January of 2017 in the chapel at Christchurch Cathedral. That was just 2 people, and photographs taken by RASC Victoria Center members were projected on the ceiling of the chapel. And the music is by William Herschel, who was a very famous astronomer, but was also an excellent musician. And but this time it will be previously unplayed symphony and a rediscovered organ concerto. And the performance will be in the main nave of the cathedral. So the pictures will not be. You will not be bending over backwards to look at your colleagues' pictures on the ceiling. And the tickets will be going on sale in the next few days for the concert.
That will mean there's some more tickets this time.
There will be more tickets, yeah.
Because that was quite limited last time, wasn't it?
It was an amazing experience. And you mentioned Alan Batten before. Alan, there's a role for narrators, and Alan narrates some text from William Herschel and Caroline, I'm sorry, I'm forgetting her last name, Caroline Herschel. So it's a very beautiful mixture of history, very beautiful and very rarely played, but lovely music, and the work of our colleagues in the Victoria Center, photography, and sketches.
Where are the tickets?
They'll be through the cathedral.
They take care of them. Yeah.
They have several outlets, but you can always buy them in the cathedral box office.
Yeah. Thank you, Jim. Yeah. Did I forget anything else? So just a reminder that after the talk, everybody's welcome to come up to the 4th floor lounge of the Elliott Building for coffee, tea, and cookies. And so now I'll ask Reg to introduce our speaker.
Do you want to
make sure everything's working again?
Well, Dr. Ninka van der Merel is getting hooked up to the sound system and the computer. I'll give it a few words. My pleasure to introduce her tonight. She joined NRC Hertzberg as a research fellow last fall. And before that, she spent 2 years in Honolulu at the University of Hawaii with their Astronomy Institute. And before that, she graduated and obtained her PhD in the University of Leiden in the Netherlands. And her interest is on basically planetary formation. She talks right here, she calls it birth cradles of planets, which we can now see with the new technological developments of ALMA. And she spends a lot of her time studying sub-millimeter signals from ALMA, from the Yankee Very Large Array, and also from a set of millimeter telescopes up on the top of Mauna Kea. And she also is trying to directly image planets as well. So exoplanets, formation of the solar system is basically her main passion. And in particular, I wasn't too, the name Leiden University kept coming up. So this afternoon, I jumped on my Google airplane and I flew across the pond and found Leiden is situated halfway between Amsterdam and The Hague. And it's about the astronomy department's about 2 kilometers away from the North Sea. And I was astonished about this university. We're just celebrating with great fanfare the 100th anniversary of the Plaska. Her observatory started in 1633. It is the oldest continuously operating observatory in the world. And it first was set up in that time to house the quadrant of Snell. Now, Snell developed Snell's law. One of the other people a couple of decades later that went there was, for a couple of years, was Huygens. Now, a number of people in our room probably have Huygens eye pieces, but I also discovered that he invented and has a patent for the pendulum clock. So we're talking way back when. And his father hung out with Galileo and René Descartes. So he was very well positioned to get into that area. So jumping ahead 300 years, one of the directors of the observatory was Einar Hertzberg. We know about the Hertzberg-Russell diagram. The person who succeeded him was Jan Oort. So I tell you, she comes from a royal line of astronomers. And so I don't know if I should introduce her as doctor or princess.
Yeah, so for later at the coffee, please call me Nienke. But I should remember that when I'm teaching. So good evening, everyone. Thank you so much for coming. So I will talk to you tonight about the topic of my research, planets and construction. But I want to start with a little anecdote about being an astronomer, because usually when I tell people that I work in astronomy, this is the image that people seem to have, that this is what I do all night, that I sleep during the day. And then at night I go to a high spot, place with a telescope, and just look up at the sky, look at all those amazing stars. And even though I enjoy doing that, don't get me wrong, this is Mauna Kea, 4,200 meters, you have a very magnificent view up there. It is also freaking cold, so I couldn't stay out for more than 5 minutes to take this picture. No, my day-to-day life is really just a 9-to-5 job. or well, it's academia, so let's say 10 to 6 job, where I work in an office at a computer and programming most of the time to reduce my data, and the few times that I go outside to watch the stars is definitely not more than any of you, or probably even less than you. And it's a second topic that often comes up when I say that I'm an astronomer, is this question, are we alone? Is there life out there in the universe? My first response to that is, I am sorry, I'm not allowed to tell you because I work for the government. And in the US people actually believe me. So I have to be a bit more careful there. But it's of course a very fascinating question. It's the origin of life, origin of astronomy. Is this fascination with the universe of, are we alone? Is there life out there? Where do we come from? So I want to talk a little bit about that, about life on other planets. So I think this quest starts with this search for exoplanets, which are planets around other stars than our sun. So at the moment, there are 3,779 exoplanets. I checked it just before this talk, because I have to update this number every time I give a talk. It always increases a little bit. On this website, exoplanets.nasa.gov, and there you can find all the information you want, the discovery and properties, everything you know about these exoplanets, and all the relevant publications about them. So what about the history here? So back in my day, so around the time I was born, we had 9 planets in our solar system. And then for a long time, we kept having 9 planets. Then in 1995, the first exoplanet, the Andromeda star, was discovered. And then the years after, we started to discover more and more and more exoplanets. So you see the number of exoplanets going up, going up. Then in 2013, oh my God, Pluto was no longer a planet. The International Astronomical Union decided that. But who cares? We had about 1,000 exoplanets, so who cares about Pluto? Oh. And the number kept rising and rising, mostly because of the Kepler satellite. And we're expecting to keep finding more planets around other stars. And the fact that there are so many planets out there means that we're actually not that special. You know, the solar system is just one of many solar systems, planetary systems in the universe. So the chances that there is life on one of those other planets is actually not that unrealistic. So then, are we actually going to find those aliens? Well, that is a different question. Sorry, I forgot this part. First of all, how do we find these exoplanets? Because finding an exoplanet is like trying to detect a firefly right next to a lighthouse. You're looking at something that's really faint right next to something that's really bright. So there are 3 main methods to find exoplanets. And I'm sure you've heard of them before. I know that my colleague Henry gave a talk here earlier this year, but I'm going to explain them to you anyway. So the first method is called the transit method. Because if a planet orbits a star and passes in front of the star, and you measure the brightness as a function of time, so you measure it every half hour, what you will see is that the brightness drops for a certain length, and then it goes up again. So this is when the planet passes in front of the star, blocking a fraction of a percentage, it's a very small amount of that brightness. And if this happens periodically, well, that is your evidence that there must be a planet there, because it's orbiting. Then a second method is called radial velocity. Because another thing that happens when a planet is orbiting a star, it is not just the gravity of the star working on the planet itself also exerts a gravitational force on the star. So the star will bubble a tiny little bit, it will move around. And this bubble we can measure because of the Doppler shift, which tells you that if something is moving away from you, light will get a little bit redshifted, and if it's moving towards you, light will get a little bit blue shifted. And this is something that we can measure. So again, if we measure the light of a star, in this case, lines, a spectrum of the light of the star, and we can measure the shift as a function of time, and in that way deduce that there must be a planet there. Then the third method is called direct imaging, using coronography. And this is actually a way to make an image of those planets. Because in this case, we put a mask in our telescope exactly at the location of the star, blocking out that really bright light of the lighthouse that I was just showing you. And then we look in the direct environment, trying to see if we find any bright blobs. And again, if we have multiple measurements, we can see that those blobs move, and they are supposed to move in a circle. That is an indicator that these are indeed planets bound to the star. And again, we have found a planet. Unfortunately, like with many things in life, size matters. So the most massive planets are the easiest to detect at any of these planets. So obviously the first planets that we found around our stars, most of them were very different than the Earth, very different than our solar system. They were multiple times the mass of Jupiter. And also many of them were actually really close to the star. This was mostly for the transit and radial velocity method. So they're actually very different than our solar system. However, with more and more development of new techniques, over the years we've become more and more sensitive, even to planets like the Earth. And we can detect those now in the same way. And that adds up to these almost 4,000 exoplanets that we have. So we have many exoplanets. Now the question, can we go visit those other planets? Can we see if there's life out there? Well, the problem is that the distances in space are really large. And I'm going to give you the numbers. So the closest star to us is the Sun, which is like 150 million kilometers away. Then there's Pluto on the other side of our solar system, which is around 30 times further away. And then the next closest star is 25,000 billion miles away from us. That's called Proxima Centauri. And yeah, these numbers don't tell you much, right? These are just a lot of zero. It's really hard to imagine how far that really is. So I'm going to express it in a different unit, because the speed of light is constant. It's 300,000 kilometers per second. So say that we express these distances in light time. So how much time it takes for the light to travel over that distance. Then the Sun is 78 light minutes away. Pluto is already more than 5 light hours away. And then our second closest star is 4.5 light years. So most of what we have in space is empty. It only takes light 4.5 light years just to get to the closest star. From the closest star to the Earth. Maybe a little bit, another comparison that you can make, say that I'm the Earth and the laptop is the Sun, so we are about half a meter away from each other. Then Proxima Centauri, that other star, is at a distance of Nanaimo. Everything else is empty, there's nothing there. So these are the distances that we're talking about. And I'm going to ask you, what is the furthest that humans have traveled? I know. The moon. Very good. And how far is the moon? 1 light second. Exactly. So you can imagine that the furthest we've traveled is 1 light second. Imagine going as far as the Sun. Humans traveling to the Sun. Traveling to Pluto. Traveling to that next star. It's impossible, right? It's so many times further away than the moon, than the furthest place that we visited so far. Okay, well, maybe we cannot travel to other planets, but maybe we can detect their existence. We can listen to radio signals and try to find out if there are other civilizations out there. Well, I think there's another problem there, and that has to do with time. Because the Earth is like 4.5 billion years old. And in the beginning of the lifetime of the Earth, there was really not that much going on. So after 1.5 billion years, people think that there were bone cell organisms. They were definitely not capable of emitting radio signals. And that sort of kept going for most of the lifetime of the Earth. So for like 4 billion years, there was nothing that was even crawling. In the last 500 million years, we got things like bacteria, and we got plants, and then eventually we got fish. And then finally, those developed into dinosaurs about 200 million years ago. And those stuck around for a long time. Then finally, we got mammals. So now we're 50 million years ago. But most of the lifetime of the Earth, there was nothing else. We're going to make another jump from 50 million years ago to 5 million years ago. This is now we're finally getting to the point to something that looks like us, that is walking on 2 legs. Just has a lot more hair. So these are the first ape-type animals. They started to walk up more straight and started to lose their hair. Homo erectus, Neanderthal. Now this scale is not linear, right? We're 100,000 years ago. We had something that looked like us, but that was definitely not that intelligent. Only 80,000 years ago, humans came around. 6,000 years ago, we find signatures of a civilized society, a society that was actually building stuff. They were still not creating radio signals. We take another jump. Now we go to the last 600 years ago. This is a plot of growth in technology. So in this case, the first technology that they mentioned here is the printing press. And then 200 years ago, yay, the telescope. It was not emitting anything, but at least it was a telescope. Steam engine, telegraph. Okay, we're starting to broadcast signals. This was only 200 years ago. A light bulb, telephone, car, man on the moon. Well, here we start to get into the computer era, and this is where we took a huge jump. But this is only in the last 50 years that technology has made such a big growth that we're actually transmitting significant signals into space. 50 years on a lifetime of 4.5 billion years. We have technology now. Well, you could say, who cares? It took a long time, but now we're here. Our sun is not gonna give up on us for another 3-4 billion years. So we have all this technology now. Now we just wait and we see if another civilization is in the same state. The problem is, as we've seen with dinosaurs, most societies or civilizations don't actually survive that long. Because there are a lot of things in nature that are out there to kill us. So there are solar flares, there are asteroids, as the dinosaurs, there are viruses, and then there are also, there are things that humans can do to each other. And since 2 years we have this guy. So the chances that a civilization lives long enough that another civilization is in the same state of technology and is able to communicate with us, those chances are actually pretty small. And that's why I think that even communicating with aliens is not very likely to happen. So, well, no aliens, so I study planet formation, which is the topic of my research. Because we can. Astronomers are all about trying to find out how things work. We're fascinated with the universe, with physics, and we just want to answer puzzles, right? We want to work with problems. And this is definitely a fascinating problem. Because we know that planet formation is a 1 million year long process. So that's a long time to wait. And I know you guys here in Victoria, you're used to waiting on construction processes. That's what I've been told. I arrived here in November, so for me this bridge was finished in 3 months, but I heard that it took a long time before that to actually get there. No, so how does this actually work? The planets form in disks, what we call these protoplanetary disks. And I like to compare these with pancakes, because they're flat and round, and you can rotate them. That's how I always visualize them. And then this is the general process. And we'll come to more of the details. So, in order to form this disk, you first have to form a star. And the star is formed inside these large diffuse clouds of gas and dust, which will collapse under their own gravity. So you get denser clouds, dense cores. Eventually, these cores are so dense and hot that we can actually call them protostars, because they start to emit their own light. Then the cloud is still collapsing further, and because there's always a little bit of rotation in this cloud, and it's collapsing, this rotation will go faster and faster. Because if you have something that is rotating slowly, like an ice skate dancer, and he puts in his arms, he is actually going to rotate faster and faster. So this works in the same way. And when something is falling inwards and rotating, it will actually flatten. You can test this with a ball of pizza dough. If you rotate it, it will actually become flat. It becomes a disc. And again, you have a pancake or a pizza, or in this case, a so-called accretion disk, because material will continue to accrete from the disk onto the star. But also, we think that in those disks, the planets are forming. So eventually, after a couple of million years, the disk will have disappeared, and then we're left with a star and with a planetary system. And then to make the circle complete, eventually any star will die, so it will explode or implode depending on its mass. And then material will be swept away, and actually it returns then to the interstellar medium. And it forms these clouds again. Then the whole process starts over. So I already mentioned that our sun is 4.5 billion years old, while the universe is about 14 billion. So the material of our solar system, or that our solar system is built from, is already the product of probably a couple of the cycles of this process. So we are made of stellar explosions from dating back to the early universe. So anyway, I want to focus here on this part of the process. How do we get from these disks to planets? And the general idea that we have of planet formation is that we need to grow dust particles. There are a lot of these tiny little dust particles. They're already present in these clouds. They're like a micrometer or smaller in size. You can imagine them like tiny little sand grains. And those particles, they are rotating in the disk. And every now and then, they may collide with another dust particle. Then there is a certain chance that they will actually stick together. And stick together. And collide and stick together. So that process will keep repeating itself. And in that way, you can grow to larger and larger particles. And it sounds very inefficient, but if you have millions of years, it turns out it's actually not too bad. There are people doing models and also doing lab experiments of this process, and it actually kind of works. You still have to grow quite a large number of steps. So you have to go from micrometer, factor 1,000 to millimeter, another factor 1,000 to a meter, another factor 1,000 to a kilometer. Well, at this stage, gravity starts to become important, and then things go really fast. But as soon as the gravitational force is strong enough, it will actually attract material very quickly, and it will form a planet like our Earth, and then maybe even something larger like a Jupiter, like a gas giant. But the biggest question in planet formation is really these early stages. How quickly can we grow dust grains to millimeter, centimeter sizes, so that we have these building blocks for the larger bodies that eventually form the planets? And a lot of the research is based on that question. And one of the problems here is that we can actually only observe particles that are in this size range. And then we can observe exoplanets that are in this size range, like the Earth, sort of size of the Earth. In between, there is no way we can observe this in other systems. We're simply not sensitive enough, at least with the current telescopes. So this part we have to guess what happens. Our models tell us that if we get to this part, like a meter, we're probably good. we can form these planets, but first we need to solve this first part. So in order to do that, we want to study these disks. We want to see what is happening inside these disks. And the problem here is that the disk itself, they're not small. You know, a typical disk is like 5 to 10 times larger than the solar system. So I express it here in AU, astronomical unit is the distance between the Earth and Sun. You will hear me use that term more often. Just try to remember that Earth-Sun distance is 1 AU. Just easier than saying millions of kilometers all the time. So 10 times larger than the solar system, that sounds pretty good. But the problem is that they are really far away. Disks or star-forming regions which contain disks are located hundreds of light years from the Earth. Because we are already 4.5 billion years old. So we have formed such a long time ago. In our neighborhoods, nothing is forming anymore. We have to go to these other areas where stars and planets are still actively forming. So hundreds of light years away, 300 AU. I'm going to give you an illustration of how tiny that is. And for that, I'm going to use Peter. So Peter is on the dating site, and he's holding a fish. And I've noticed that in Canada, that guys on dating sites here, they like to hold fish. Because that is every girl's dream, right? The guy who can catch a fish. That is actually very useful in this case. It is because so Peter's holding this large fish, like a meter, 1.5 meter, and now I'm going to ask him to climb Mount Baker for me because well, he needs to do something then to impress me. So he is going to climb Mount Baker. I'm going to the observatory up here in Victoria, and I'm going to look at Peter. This is about 120, 130 kilometers away. The size of that fish, that is the size of a protoplanetary disk at 400 light years. That angular scale is what we're talking about. And we're not just trying to see the fish, we actually want to see all the details, right? We want to see what's happening inside that disk, inside that fish. And you can say, well, who cares? Because you have telescopes, you're not looking with your eyes. You actually have, you can see a lot more than what our eyes can do. Well, the problem is that even with telescopes, there are some limitations. And in this case, that limitation is resolution, or the level of detail that we can see. And the amount of detail that's a very simple rule. It's just determined by the wavelength that you're observing divided by the diameter of your telescope. So the larger your telescope, the smaller detail you can see. Okay, so that's nice. But the protoplanetary disks, they are made of really cold material, which means that they are emitting in the radio wavelengths. And so radio is located over here in the spectrum. So we have, here's the visible light, so like 400 to 700 nanometers. Then if we go to longer wavelengths, we call it infrared. So now we're talking micrometer, 10 micrometer. And if we go even beyond that, we call it radio waves. And I would like to add here that radio is just, it's a way to describe the technology that we use to detect these wavelengths. It has nothing to do with listening to the radio. So I don't know how many of you have seen this movie Contact, where you see Jodie Foster with her headphones next to the very large array listening to the radio signals. Well, I did the same thing when I was there last year, and it was, yeah, obviously didn't hear anything. But I just want to clarify, this term radio wave is the technology, because you can only detect these kind of frequencies, these kind of wavelengths with a radio technique. And in this case, we're for protoplanetary disk, we are looking at specifically millimeter and centimeter waves. That is where these disks are emitting most of their emission. So if we want to observe with this case a 30-meter telescope, it's a 30-meter diameter, it's located in Spain. and we want to observe at a millimeter wavelength. The smallest detail we can see is a lot larger than that fish. In fact, if Peter is standing there on Mount Baker, and he does this, like to make himself as wide as he is tall, and say that he's 2 meters, we still won't be able to see him. He would still be a blob to us with a telescope like this. So there's no way that with a single dish telescope, we can see the detail in that fish, in that protoplanetary disk. And there's no way that we can resolve the structures that tell us something about planet formation. So luckily there's a solution, and that solution is called ALMA. So ALMA stands for Atacama Large Millimeter Submillimeter Array, which is an array of telescopes, not a single one. It actually consists of 66 telescopes that are working all together in order to resolve structures in more detail. So ALMA is located up here in the north of Chile, in the Atacama Desert, at 5,100 meters elevation. You can see here, I mean, it's kind of a plateau, so it doesn't even look that high. And you're surrounded by mountains that are even higher. But you definitely feel it when you're walking around there, that there's not much oxygen and that you're actually really high. And this picture gives you an idea of how large the telescopes itself are. Remember, there are 66 antennas like this, and they all had to be transported up there. Roads had to be built. Construction sites had to be developed just in order to build this telescope. And here are a couple of humans right next to it. So it tells you a little bit about the scale of this operation. So this array started its operations in 2011, which was the starting year of my PhD, so I was very lucky. The ALMA project is a global collaboration between Europe, North America, Chile, and East Asia, and Canada is obviously a partner in North America. The budget of the telescope is about $1.3 billion, so it's similar to a space mission, but it will have an operation of about 30 years, so that's quite a lot longer than most space missions. The sensitivity, so the amount of signal that we can detect with this telescope, is 100 times higher than any previous interferometer. So similar kind of arrays that were smaller. So it means that we can detect a lot fainter sources. But more importantly, the distances between the telescopes, which is what we call baselines, go up to 16 kilometers. And if you use an array like this, the distance between telescopes actually determines the amount of resolution, the amount of detail you can see. And in this case, the baseline up to 16 kilometers tells us that we can have a resolution of only a few astronomical units, so really of the size of the solar system. And the wavelength coverage, so the wavelengths that we can observe with it, range between 0.3 and 3 millimeter. So the perfect coverage for studying protoplanetary disks. So how does this work with an array? I don't want to go into too much detail because honestly that involves a lot of math and I don't want you to fall asleep. So the technique that ALMA uses is called interferometry. And it's based on the idea that light is traveling as a wave. So we have a distant source and waves are coming from that source towards the Earth. Then you can imagine that wavefront arrives earlier at telescope 2 than at telescope 1. So, and when it detects it, it actually records both the amplitude and the phase of that wave. And then it combines that light between two telescopes using that information. So, because we know the exact distance between the telescopes, and because we measure the phase in each location, we can measure tiny details, tiny little variations in structure at the distance of our sources. And that is what we call interferometry. And with that technique, if we go back to Peter, again going up to Mount Baker, he can now bring Nemo and Dory up to that mountain, and we will be able to see them. we will actually be able to see the color of the eye of Nemo when we're standing here at the observatory, at Observatory Hill, when we look at it with our ALMA eyes. So that means that we finally have the power to look at these protoplanetary disks and see all the structures inside of them and see what's happening there, what are indicators of the planet formation process. So what are the things that we can observe? Well, there are dust grains, or dust, and yeah, this is just the best way to visualize that, just pieces of dust like you find under the bed. And we can also observe gas, or better to say, we can observe molecules. And I want to explain a little bit of how that works. Feel free to ask me about that either during the talk or afterwards. So the way that we know dust in space is actually mostly through these beautiful images. So these are images that are taken in the visible light, where we see dust in absorption, because dust is actually not emitting invisible wavelengths. It absorbs the visible light and then blocks everything behind it. That's why we see these dust clouds that are absorbing the light behind. But when it absorbs the light, it actually heats up, which means that it will then be able to emit the light at longer wavelengths. And the way that it works is through something that we call a black body. So a black body is a way to describe an object that has a certain temperature. And it works for any temperature. So, for example, here is the sun. The sun is about 6,000 Kelvin in temperature. That means that it will emit light as a function of wavelength, so you can measure it at multiple wavelengths. And it's the brightest over here, exactly in the visible, which is why our eyes are adapted to that wavelength range, because that is where our sun is shining the brightest. And if we go to colder objects, like a star of 3,000 Kelvin, we would actually see that it emits the brightest in the near infrared at longer wavelengths. And this will just keep going. You can calculate this black body curve for any temperature you want. And you will see that the colder it gets, the further away the peak is towards longer wavelengths. So if we have something that is like 100 Kelvin, which is the typical temperature of a protoplanetary disk, even down to 50 Kelvin, we will see that it emits the strongest at like 100 micrometer or even longer. So that is where we want to do our observations, because that is where these dust particles are emitting. They emit at the temperature that they have. And so a way to illustrate that, if you're losing me here at this point, don't worry too much. Just remember that we can observe dust, and we'll come back to beautiful images later. I just like to explain a bit of the technical details here. If you think of a protoplanetary disk, which has dust, this is like a cut through a disk. You look at it from the side. The star is here in the middle. And then there's dust located here, a bit further away, a bit further away, a bit further away. And you can imagine that the dust that is very close to the star gets heated up to higher temperatures than dust that is further away. So the dust that is located here will emit as a black body up here with a peak at like 5 micrometers. Then over here it will emit like a black body at 20 micrometers. And out here, sort of the bulk of the disk, is peaking at several hundred micrometers or even millimeters. So you can imagine a disk dust emission as a superposition, the sum of many of these black bodies, all at different temperatures. And you can measure their emission to derive more information about their dust. Then the gas, it's a whole different story. So I already mentioned that if we want to observe gas, we want to observe molecules, molecular ions. And what kind of molecules do we have in space? In order to say something about that, it's good to be reminded of the periodical table of astronomy, which kind of looks like this.
because most of the universe is just hydrogen. It's actually really boring. And there's not that much you can do with hydrogen. You can form molecular hydrogen, which is 2 H atoms connected to each other, and that's about it. Then there's also quite a bit of helium, because that's the first product in nuclear fusion. And then there are tiny, tiny bits of carbon, nitrogen, oxygen that are formed in more of course, of stars like our sun. But really, there's not that much of it available. So if you start thinking about molecules that are available, you have to keep in mind that most of it will be made of hydrogen. So the molecules that we have observed in space are primarily simple molecules that consist of these elements. The most common is obviously molecular hydrogen, because, well, most of matter is hydrogen. Then the second most abundant molecule is carbon monoxide. And that is actually 10,000 times less abundant than molecular. But it is the second in line. Then after that, we get all these other molecules like CO2, water, cyanide, OH, CH+, H2O+, etc. But all of these are even more rare than CO. So this is just to give you a bit of feeling of chemistry in space, which is also a topic of my research. Chemistry in space is rather simple because there's simply not that much around. And complex molecules like we find on Earth are actually really rare, and they're not commonly found. So how do you observe these molecules? Well, it goes through molecular lines. So they look like this for anyone who's done spectroscopy. So just like a peak as a function of frequency or wavelength. And well, why are they emitting? Well, this has to do with a quantum mechanical process. Because if you have a lot of molecules together, like you have a gas cloud, and it has a certain temperature, that means that the molecules are moving around, just randomly moving around. Then they can collide with each other, and at every collision, they will transfer energy. So this kinetic energy from the movement will be transferred into energy, raising the quantum state. So you put these molecules into excited states with a slightly higher energy. And then through a process called spontaneous emission, the molecule loses that energy by emitting a photon. And that photon has a frequency or energy level that is very specific for that molecule. And you can actually calculate these things. I mean, if you're a chemist and you're really good at these kind of calculations. I cannot do it. I just look up the numbers. But the point is that if you measure a molecular line at a certain frequency, you can look up exactly which molecule it belongs to, because it's always unique for one specific molecule. And in that way, we can detect molecules and even derive information about the temperature and density of the gas. For example, inside these protoplanetary disks. This is another example. So this is not just one molecular line, but a spectrum of many molecular lines. And what is cool about molecular lines is that you can actually use them not only to derive density and temperature, but also movements of the gas. So I already mentioned that disks are rotating. So that means that if a disk is slightly inclined, you will have one part of the disk moving away from you, and the other part of the disk is moving towards us. So this part will be redshifted, and the other side will be blue shifted due to the Doppler effect. And this is something, again, you can measure in molecular line emission. So this is kind of how that works. In this case, you look at the molecular line, and you see that it's not just a simple Gaussian. You actually get this red component at one velocity and a blue component at the other velocity, all from the same disk. And say that you have the resolution that you can zoom in onto this disk. You even can resolve this kinematics, so you can see this is a scan through the different velocities in the disk. these are the ones very close to the star, blue shifted, again to larger and larger velocities. On the other side, going to the red velocities. This is the kinematic pattern of the rotation of a disk, which is something that we barely could do before ALMA, but now with ALMA we can. This is actually fine. So this is something really amazing, because of course we knew that disks were rotating, and that was the only logical way. But actually seeing that for the first time, and seeing that, you know, physics makes sense, for me that was incredible. Yeah, one of those images, I think this came out in the second year of my PhD, and that was like, wow. Like I said, physics works. So some of the discoveries that ALMA has made, I think this is one of the most spectacular ones of the last couple of years. So these are dust images, of some of the brightest disks. And what we see is that these disks are actually not smooth like pancakes. They consist of many rings and gaps, which indicates that planets are already there, and that planets have actually carved gaps in these disks. And then we can measure the size of these gaps and the depth of these gaps in order to derive more information about these planets. Remember, detecting planets directly is really hard, but in this way we can derive indirect information about them, and that we still understand a little bit more about their formation process. Sorry. Because the fact that we find them in systems that are really young, for example, 1 million years old, that means that planets must form in less than that amount of time. And in that way we can constrain our planet formation models. Yeah, whatever happens, we have to be able to form them in less than 1 million years. Then another type of objects that we've seen in this, and this is really the topic of my PhD, so I want to spend a little bit more time on this because I think it's super cool. Is that a lot of these disks they don't just have multiple rings, they actually have these cleared inner regions, they have these large cavities, and they're surrounded by large scale rings, but even asymmetric rings. And these asymmetric rings, so like for example this one or this one, but even the rings itself, we think that they are consistent with so-called dust traps, places where dust is concentrated and dust growth is enhanced. And in order to explain that, I have to take you back to how we used to think that dust growth happened. So, say that you have a smooth disk. This is how we used to think that disks looked like before ALMA. And there were all these dust particles, and the particles collided sometimes, and then were able to stick together. We call it coagulation. They could also collide and then fragment into smaller parts, but there is a balance between how much they stick together and how much they fragment, so that was sort of a way to balance the dust growth processes. And in that way, we were trying to explain planet formation, that there was this balance, but slowly you could grow to larger particles. However, there was a second process that was calculated that is called radial inward drift. And that is caused by the fact that there is not just dust, but also gas present in the disk. And I'm trying to illustrate that in this figure over here. So say we have a disk. Well, the gas density is the highest close to the star, and it drops off as a function of radius. That the fact that you have this drop-off in density results in a gradient in the pressure, just a property of gas. That density scales with pressure. And also the temperature is higher in the center than in the outside. So this results in this pressure force. And the result is that things that are rotating, of course they feel the gravity from the star in the center, but they also feel that pressure. The pressure gradient and the force as a result. That means that they will orbit slightly slower than they should, based on the laws of Kepler. So if there was only gravity, they would follow Keplerian motion. But because there's also pressure gradients, they will go sub-capillary, 0.1% slower than capillary. So this is not, you cannot measure it. But you can put it in a model and see what it does to your overall system. And that is actually quite important if you look at dust particles. Because small dust particles, they are comparable size or only a little bit larger than gas molecules, right? So we call them coupled to the gas. They will also move slower than capillary. However, if you have dust particles that have grown to larger sizes, they get decoupled from the gas. So they don't feel that pressure gradient anymore. They just want to move capillary. But they're surrounded by all this other material, all this gas, all these small dust particles that are moving slightly slower. So they feel some kind of headwind or friction. And as soon as you feel that and you're rotating, you actually lose your angular momentum and you drift inwards. Is that the moment that dust particles grow to millimeter sizes or beyond, they immediately drift into the star. And this was, of course, a huge problem if you want to understand planet formation, because if you cannot grow beyond a millimeter, you can never grow all the way to a planet, right? The counterintuitive process here is that the large dust particles, will always move towards high pressure because of this radial drift problem. So how can we grow dust particles? Well, what we need is a high pressure region in the outer part of the disk. So in that case, the dust particles will move towards that high pressure region, and then we start there. How can you create a pressure region like that? So one thing that was suggested by theorists was that, say that you could form a planet somehow. We're not going to worry about that. How that happened, but say the first planet was formed. It's located at a certain distance from the star. So this is a gas density as a function of radius. So the star is, here. The star is over here, and my planet is located over here. Putting in that planet lowers the gas density along its orbit. And you get this dip in the gas surface density in sort of a ring. Then along the edge of the gap that the planet has created, you get this bump in density, right? And this is exactly what we needed. We needed a bump in density or a bump in pressure where the dust particles will drift towards that pressure maximum. And then we stuck there. And then they can continue growing to even larger particles and maybe even further planets. And this is maybe a bit hard to imagine, but say that you convert this back to a two-dimensional image. Having all dust particles at a specific radius is the same as all dust particles in a certain ring, which is exactly what we were seeing with ALMA, all these dust rings. Even better, these radial pressure bumps in certain circumstances can become RASC unstable. And I have a little movie of that. Let's show over here. So we see a star and a planet. The planet is orbiting the star. This is in a disk. And we see that it starts to trigger a bit of spiral arms. But also you see that the planet starts to carve a gap. You see that it gets darker along its orbit. That means that the density goes down, so it's carving a gap. And at the edge of that gap, you see that you get this, bit of spiraling motion, but it keeps going. It's a little slow simulation. But you start to see that you get these clumps of density. This is this RASC wave instability that I was talking about. This is a vortex. And this may sound a lot like magic, but we're actually all aware of RASC wave instabilities because you see them every time you pour milk in your coffee or in your tea. But you see these spiraling motions. That is the result of fluid dynamics, of two fluids with different densities streaming alongside each other, triggering this instability. And the same thing happens in the disk when it's, a gap is cleared by a planet. This Rossby instability can start to develop. In this case, you no longer, you also have this density pressure bump, but not only in the radial direction, but also along the ring direction. And in that way, you can get these azimuthal asymmetries that we were seeing in this, in this image over here. So remember what I told you, all these rings that we're seeing, they're just radial pressure bumps, radial dust traps, probably as the result of a planet. And then in special circumstances, this dust trap can become Rossby unstable and form a vortex, which traps the dust like this. This discovery of this phenomenon in observations. I mean, this was already predicted by theory that maybe that was a way to solve the dust growth problem, but it was never observed before. And Alma showed us that this was really happening. We discovered that these dust traps really existed. Here we go. Because it's actually this specific disk that was the first one where we found clear evidence that it had to be a dust trap. So we see millimeter dust in very asymmetric distribution. And here it's located. Here's millimeter dust is shown in green. It's the same source. We already had observations of micrometer dust, so an infrared image that was showing a ring. The fact that the micrometer dust was still showing a ring and the millimeter dust was concentrated tells you that dust is actually larger dust particles are being trapped while smaller particles are not. And this was an incredible discovery that I made actually in 2013, one of the first big ALMA results. And it's amazing how much consequences this has had for our understanding of planet formation. Because we found many more disks that are showing similar kind of structures. Either extreme asymmetries or some minor asymmetries. And it shows dust growth as a phenomenon and dust trapping as a way to explain dust growth in protoplanetary disks. Okay, so completely other ALMA discovery. Other things that we've also seen in disks is that there are spiral arms in disks, so just like in galaxies. And a spiral arm in millimeter dust can only be explained as a gravitational instability. So this is again a process that just happens because of the dynamics in the disk. But in this case, due to the gravity of the disk itself. That happens when the disk mass is, well, on the order of the mass of the star, or maybe half of the mass of the star, that it becomes gravitationally unstable. Because in that case, the gravitational forces are no longer just dominated by the star, but also by the material of the disk. And that triggers the formation of these spiral arms. We also see disks, so the ones that have these nice dust rings. When we're observing them in the gas, we actually see that the gas and the dust are distributed differently. Which is, I mean, that's part of this whole scenario of the dust trapping, the fact that the dust is concentrated and the gas is not. But it also shows you that disks are dynamic. They are developing during their lifetime, and things are changing throughout the disk lifetime. Another cool thing, so I already mentioned that disks are, Keplerian, they're rotating. And indeed, some disks were doing that. So here we see the velocity in a disk, where on one side is blue shifted and on the other side is red shifted, exactly as we expect. But there are also some disks that are doing crazy things in the center. So here, if you look at the outer parts, it kind of looks similar as that disk, right? So it just, here it's red and there it's blue. But then close to the star, it's all warped. And we think that this is related to a misalignment in the disk. So the inner part has a different orientation than the outer part, which is again related to companions being present in the disk that are messing up the whole system. This is actually still a big question of what's really going on here. There's a lot of active research on this. There's also theories that say that it's not just misalignment, but also gas being accreted onto the star, and that is what we're measuring: large-scale gas streamers going through the disk. And finally, a thing that we can do with ALMA is, because they're so sensitive, is detecting molecules, not just CO, but actually much more exotic molecules as well. And it means that we can do astrochemistry. We can start to study chemical processes in disks and understand how these molecules form and maybe even end up on planets. And I like to show this because it's actually a very simple phenomenon. There's a molecule, it's called N2H+. I don't know if there's a layman term for it, it's called N2H+. So it's 2 nitrogen and 1 hydrogen atom. And N2H+ is a molecule that can only form if there's no CO. Because if CO is present, it will immediately react with it and destroy it into other molecules again. But the thing is that at a certain temperature, or actually below a certain temperature, which is about 25 Kelvin, CO will freeze out onto the dust grains. This is again something we can measure it in a lab. We can experiment with this, and we can now also observe it in the disk. Because what we see, this is the CO emission in a certain disk. You see that it's very bright, close to the star, and then it drops off further out. And then we see that this molecule, N2H+, starts to pop up at about 40, well, maybe 30 AU from the center. And this, the way that we understand this molecule is that it only can form when CO is frozen out. So this tells us exactly where CO is frozen out, or where the temperature is equal to 25 Kelvin. This is amazing. We can measure the temperature in this at a certain basis. This is something that we're now capable of doing for other molecules as well, so also for other strobites in disks. And finally, all these crazy molecules I already mentioned, if molecules get more and more complex, eventually they form building blocks of life. So at some point, we may be at a stage where we can really relate molecules in disks to starting life on planets, because eventually they have to end up there. I would always like to end with this note from Kelvin. Because Kelvin screams at the sky, "I'm significant." And then he realized that he is just a dust speck. He's very tiny compared to the universe. And he's right, we are very tiny, and most things in space are really far away and are much bigger than us. But the fact that we have our technology and that we have telescopes like ALMA allows us to study what's happening in space. And that makes us at least a little bit more significant. And definitely makes it worth it for me to work in astronomy. Thank you for your time.
Thank you so much for what a very interesting talk. It's amazing what this new instruments can do. And it seems like you arrived on the scene just in the nick of time. Perfect to solve your problem. I'm sure there's some questions out there. I have one. So when you have this big clump of dust there, is that going to accelerate planet formation in that wall?
Yes,
and that's going to change the whole ballgame trying to predict the frequency and the speed at which solar systems are formed.
Yes.
Wow. Congratulations on that discovery. It's pretty big. Has anyone got any questions for
I was curious, when you have that pressure bump that creates a dust trap,
Mhm.
when that basically you get that spiral motion and it clears it out, would that basically increase the chances of other planetaries forming the next ring?
Yeah, exactly. And then it is also a bit of a problem, right? Because it's a chicken and egg. You need a first planet to create those pressure bumps that then form the next planet. And we don't know how to solve that. But say that due to whatever circumstances that first planet is formed, then we can explain the other planets further out. So it's definitely a way to enhance the process.
And you wouldn't know whether or not that's going to be the biggest planet of the solar system or the closest to the sun.
Not necessarily. So any planet will trigger these pressure bumps. Smaller planets will create very tiny pressure bumps. Maybe they don't live very long, or maybe they are dissipating very quickly, or it takes very long for the dust to concentrate in those because there are only minor variations. But it does help in a certain way. And another thing to keep in mind is that even if planets form at a certain location, if there's still a lot of disk material around them, the disk material exerts a torque onto a planet, and that can actually result in the planet migrating inwards or outwards, depending on the local conditions. So in that way, you can still change the entire configuration of your solar system. Other mechanisms, and this is how we generally understand the solar system, can even migrate planets or scatter planets after the gas in the disk is gone. So these are more related to resonances and things like the Kuiper belt that move around planets on longer time scales. So the formation location of the planet is definitely not related to where the planet is now, both in our solar system and in other exoplanetary systems.
The N2H plus that you described, is that connected to pre-life or life as we know it? Or is that
N2H
stretching
plus
too
not
far?
directly.
Okay.
I mean, once you have N2H plus, I don't know the chemical reactions by heart, but you could eventually relate any nitrogen molecule to, for example, CH3CN. That is already a bit more like a molecule that is related to building blocks. But it's still a long way to get to these building blocks. And the problem is if you get to larger molecules, they become more rare, which means that they are harder to detect. So most likely the path to our building blocks remains at the starting point. Just what kind of molecules can we find? And it remains a theoretical problem. How do they turn into building block supply?
I have two questions. One is perhaps more professional, one perhaps more personal.
Mm-hmm.
I think I'll throw them both at you. You choose how you'd like to answer it. Professionally, you're at a great point in your career. You've had access to an amazing instrument. Where would you like to see that go? And then the second question is, as a woman astronomer, you've taken a certain path to get to where you are. I've spent a lot of time over the past year visiting other RASC centers and other organizations and trying to find ways to encourage young people, especially women, to go into science, engineering, and the other STEM disciplines. I'd be interested in any thoughts you would have on that.
Just a second, before you answer the question, I'd like to introduce the person who asked the question, who just came in. This is my friend, Colin Haig, who is my immediate predecessor as national president. He's from the Hamilton Center, but he happens to be in town on business. So I hope everybody makes him welcome, and I'll let you answer your question.
Yeah, so well, let me first answer your first question. I guess that's easier. My dream is, of course, to continue working in astronomy. I hope to get a permanent position within the next couple of years. I have to say I really love Victoria, so I hope I will be able to work here, either at Herzberg or at the university. So I guess that's where most of my energy goes these days, to convince them that I'm really good at what I do and I can contribute to astronomy here. On the second question about being a woman in astronomy, I feel there's definitely a problem in the academic system as it is right now because of the way that we have to work. So after our PhD, we have to do these postdoc positions. So that is what positions I'm doing now. They are temporary. They are all over the world. They are hard to get. They're very competitive. And you are expected to do at least 2, these days maybe even 3, before you are even considered for a permanent position. The age at which you are doing these postdocs is your early 30s, and that is also the time that most people want to start a family. Well, I don't have a family right now, and I hope I will be able to someday, but at the moment I have chosen to focus on my career. I think this is one of the major things that would have to change in the academic system to give women better chances. Because what we see is at the undergrad level, a lot of more and more girls choose to study science. But at the higher levels, it becomes harder and harder because of these kind of decisions. And I hope that is something that will change. I don't think there's any difference in capabilities or even passion for science. I think that's totally the same for men and women. There may still be a bit of an image problem that science and especially astronomy is difficult, or that only old white professor guys in ivory towers are capable of doing it. Well, that is one of the reasons why I like to do these public talks, to show that everyone can do astronomy, and you just need a certain amount of enthusiasm and passion in order to work in this field. But the career steps is something that, well, I don't have the power to change it. I just hope that's something I will be able to.
Well, I'm very optimistic about it. As past president now, I've got the benefit of 20/20 hindsight, and this guy gets all the problems. But I noticed in our membership, as I would visit centers, and I've been on the board long past my expiry date, I think. Just in the last 8-10 years, it used to be I'd come to a meeting and it would be full, and please excuse me, gentlemen, of, gray-haired, middle-aged white guys. And in our case, the RASC wasn't even representative of the academic population. The number of women that I would see at meetings would be 5 to 7% a decade ago. Today, I'm looking around this room and I see much better representation. The young people aren't coming to our meetings because I think they're too late, or they've got to drag mom or dad with them, or they're busy with university or starting their careers. But I've noticed the shift, greater diversity in our membership, and as I've met people in academia, I'm seeing that the shift is happening at the undergrad level, and I also think it's happening at the grad and then faculty level as well. It's just time it takes for these changes are quite long. So I consider a beacon for a lot of people, and thank you for what you're doing.
Yep.
Are there any more questions? Dorothy?
Well, I have a question that I ask later, but I'd just like to say, because I forgot to say that 17th to 22nd is nationwide science literacy week. And so these events that are happening, including the Nature House, are science literacy week events attempting to draw all young people, and especially women. And like you, I wanted to do science first, and family and all that stuff later. But so that's coming up 2 weeks from now. So pay attention to what's happening in Victoria for that and participate if you can.
Okay, so calling about the age discrimination, I think that a lot of people require time and they're retired and they love coming into astronomy at that level. But we have in our center a young gentleman who is 11 years old, and next issue of Sky News are going to be featuring a series of his planetary photos that he took this summer. And we're really excited about the joy that he is experiencing. So it's not a bunch of old guys. Are there any more questions? See here. Well, as a token of thanks, we have a coveted T-shirt of the Victoria Center of RASC for you, and we have it in a variety of sizes.
Thank you.
Thank you so much for taking the time.